this recording, I'm going to talk about how to find the force because of a continuous mass distribution on a point mass. We've already seen that for 2-point masses, I like to use capital M and little m. The force on little m is negative g, big M, little m over r squared times r hat. R, of course, is the distance between the 2 points. And in this case, since I'm finding the force on little m, r vector goes from big M to little m. And r hat, of course, is the same direction as r vector. If we have lots of point masses, I'm going to use the capital M's for those, M1, M2, M3 on my drawing, but it could be as many as you want, up to Mn. You just take the forces between each pair that includes the little m, if you want the force on little m, and then add them all up. So the force on little m equals the force because of m1 on m, plus the force plus of m2 on m, plus all of them, however many you have, up to the force of mass n on m. You do have to keep track of direction. That's a vector equation because, of course, each one of those, I've drawn the r vectors in the picture, and the force is the negative of those r vectors. So I could draw that real quick, I guess. The force on each one of those, so like F1 would be that direction. It's kind of hard to see. That's an F1. That would be F2 because the negative sign flips the directions, and that would be F3. So the forces on each of those would be the opposite directions as I've shown there. Oh, that's called the principle of superposition when you add up a bunch of forces like that. When I say continuous mass, it's usually just a solid object, so anything bigger than a point particle. Examples would include things like spheres, cubes, rings, hoops, discs, donuts, cylinders, basically anything you can think of. And those can be solid too. Solid or hollow, but anything bigger than a point mass. So as long as it's more than a point mass, it would fall under this category, and you'd have to do this procedure if you needed to find the force because of it. So the big idea when dealing with a solid object, so we went from 1 point mass to multiple point masses, and when we had multiple point masses, we just added them all up. So the big idea here is we're going to imagine chopping up the continuous mass into very many, very tiny pieces of mass. I'm going to call each one of those pieces dm, for little teeny tiny piece of mass, infinitesimally small. You probably can see where this is going. And then I'm going to treat each dm as if it were a point particle or a point mass. The sum goes to an integral, and the big M's become the dm, and I'm going to integrate over the dm's, which is like adding up all the dm's. Here's a picture of a particular dm, so we'll just do a weird random shape there. A particular dm, and then, which is the shaded in part of the drawing there. So this guy right here, the shaded in part of that drawing right there is what I'm talking about. And that little piece of mass, dm, which is part of the whole solid thing, is going to cause a force on that little m. So I'm basically pretending like that dm and that m are point particles. Eventually, I have to move that dm around so that I cover the entire object. But for right now, we're just thinking about that one little piece dm, and we're treating it like a point particle. I've stopped the picture here. I'm going to actually draw more arrows on that picture. It turns out we need 3 different r's. And I'm going to introduce a new scripty symbol, scripty r. The scripty r goes from, so this one right here, the scripty r goes from the dm to the little m that you're calculating the force on. Then there's the r prime. We use primes to go from the origin to the dm, so to the continuous object, basically. And then that leaves the regular r. So the regular r is the regular is the regular position vector r in 3D. So r goes from the origin to the mass, the little m, the one that you are finding the force on. Choosing these symbols is a convention I got from David Griffith's E&M book, and I really like it, so it's what I use. There's the same kind of idea here if you would be doing continuous charge distributions instead of continuous objects, continuous masses. So that's where I got that idea from. Okay, so we have to remember this picture a little bit. So the next thing I'm going to talk about is the R's, but I just ran out of space on this page. So if you look back at my drawing, the way I have it drawn, this is R, and then that one is head to toe with this scripty R, and if you add vectors head to toe, the resultant is the regular old symbol R that we're used to using, lowercase r. So those two vectors add up to be the third, and that's the next equation that I'll write, but it goes on to the next page. So those two vectors add up to be the third. So there we have it, the r prime plus scripty r equals the regular r. That's exactly what I just said when I had the picture in front of us. Now we're finally ready to write down the little piece of the force which I had drawn on that picture. It's not so hard to go back there. So that little piece of the force, I'll show you the arrow, is equal to negative. The negative sign goes with the r hat, so that's what makes it go the opposite direction. So the negative r hat, and then g, the little m we're finding the force on, the dm, the piece of the continuous mass we're treating as a point particle for right now, and then scripty r is the vector that goes from the one to the other. Yeah, I can flip back. I'll flip back real quick. So there we flip back just to see the picture, and there in black, I have labeled the .df that goes with that one right there. So that's the opposite direction from the scripty r vector that we were just talking about. Just have to let it redraw. So that's where we were. Now, so that df, so all I need to do is integrate that. I integrate df, so integrate both sides of that equation, and I'd have the total f acting on little m. That's great, except that I need to know how to write dm. dm needs to be written as coordinate variables before I can do that integration. There's another, this is a pretty standard convention of how to write these things. And it's different depending on whether it's a line, a surface, or a volume. And if it's a line, the standard symbol that we use for the linear charge density is lambda. So you get that dm equals lambda dl. Lambda may or may not be a constant. That's something you also have to know. You have to be able to plug that in before you can do the integral. We'll talk a lot more about that later. dm for surfaces or areas, so I use the two letters. S for surface gives me the Greek letter sigma there, so sigma dA, and then I often use an A for area. And then if you have a 3D shape or a volume, dm equals rho dv. Before we can still integrate, one more step, that dl, I deliberately did not write dx there, say, although dx would be a perfectly good dl in Cartesian coordinates. But we need to review all the coordinate systems because you need to have all of them in your toolbox in case any problem has a different symmetry. So the example I list right there for a cube, a volume element of dx, dy, dz is a great choice. That's not such a good choice for a sphere, for example. So depending on the problem, you need to choose a different set of coordinates, and it will make the problem a lot easier. So that's up next. I'll separate those. I think I'll do a video for each of Cartesian or rectangular, and then spherical, and then cylindrical. That's up next, and then we'll come back to solving problems with this new method.